Okay, guys, so this is the best way I found to have my iPad and a video of me within the same recording. This is quiz homework problem number 9, and it's about static fluids, buoyant force. Let's read it. An object weighing 303 newtons in air is immersed in water after being tied to a string connected to a balance. The scale now reads 267 newtons. Immersed in oil, the object appears to weigh 279 newtons. Find the density of the object. Answer in units of kilograms per meter cubed. So the wording of this problem, I found it very confusing. And what I'm going to do is I'm going to model this slightly differently. So I don't really know what they mean with the balance thing. So what I did is I instead have the object being tied to a spring scale, of course. This is pulling down on the spring scale by means of its weight. The object has weight, so let's add that force vector. That's the weight of the object. Let's call it mg. And of course, because it's tied to a string, there's going to be a tension force, and that tension force is measured by the spring. So like that. And when it's submerged in water, what the water is doing is pushing, but the buoyant force is pushing the object upward. So we can, I know this is not like the free body diagrams we usually draw because I have this arrow here. This arrow represents the buoyant force. Let's call that FB. That's the buoyant force. And it's pushing the object upward. That's why this reading becomes less, because there's an additional force pushing upward on the object. Okay? So now let's write down what we know. That is our given. Okay, so let me clarify. I have weight for the object, that is when it's not submerged in water, and then I have the apparent weight. What that means is now the object, after being submerged in water, appears to have a weight of 267 newtons. And that's going to help us find the buoyant force. Okay. So the first thing, and we need to find the density of the object. Anything related to the object, I'm going to leave without a subscript. Let me just say, this is the object. Okay, let's think about the buoyant force. Well, the buoyant force is equal to the weight of the displaced fluid. Because we're submerging this object in water, this object is pushing the water, and the water is pushing back. So the volume of water that is displaced will be equal to the volume of the object. Okay, so let's write down the formula for buoyant force. Let me use a different color here. So buoyant force is equal to the weight of the displaced fluid. And how can we know that weight? Well, that's simple, because if the apparent weight is now 267 and its original weight was 303, that difference is the weight of the displaced fluid. That's the force with which the water is pushing, because there was a push on the water of the same amount. Okay, so then we can say that the buoyant force is equal to the original weight minus the apparent weight. I think I'm spelling apparent correctly, hopefully. When we find this difference, we're going to get the weight of the displaced fluid. Okay? So let's plug in our numbers real quick, find a numerical answer. The buoyant force is going to be 303 newtons minus, what is it, 267? Yes, 267 newtons. And that's going to give us 36, I mean. Okay. So now, let's see what we can do with this. Well, we know that the weight of anything, so just weight in general, is equal to the mass of whatever object we have, whatever fluid, times the acceleration of gravity. Well, then we can say that the weight of the displaced fluid, in this case the water, would be the mass of the water times the acceleration of gravity. And we know how to describe the mass of a fluid by means of, or in terms of its density, because density is equal to mass divided by volume. Then we can say that the mass of the water, for this case, is going to be the density of the water times the volume of the water. What I did is I simply multiplied in this equation both sides by volume, and then I ended up with mass is equal to density times volume. And this is great because this volume is the volume of the water that was displaced. Well, how much water was displaced? The same amount or the same volume as the object. So if we find the volume for the water, we're going to find the volume for the object. So let's write it down. Why would we want to find the volume of the object? Well, because we know how to describe volume in terms of density, and we need to find density. So let's find the volume of the water. That's why I didn't put a W for volume, because it's going to be the same for water and object. So let's find that volume. So now we have that the weight of the displaced fluid is equal to, instead of the mass, I'm going to write density of the water times the volume times the acceleration of gravity. Okay. So let's solve for volume. We divide by density of water and acceleration of gravity, both sides. And now we have that the volume is equal to the weight of the water, which was displaced, times the density of the water, times the acceleration of gravity. And this is going to be also the volume for the object, okay? Same volume. So that means if we want to find the density of the object, so just like that, no subscript, it's going to be the mass of the object divided by the volume of the object. Now, how do we find the mass of the object? Well, we're given the weight of the object before it was submerged in water. This is its weight. We can use this quantity to find the mass. You can find it numerically, but I'm going to use the definition for weight, okay? And I'm going to say that the mass, if I divide both sides by g, is equal to the weight of an object divided by the acceleration of gravity. So then, because we know that the mass of this object is going to be its weight divided by acceleration of gravity, we can combine this equation and this one, and then solve for density. It'll look as follows. So now we have, I know this looks messy, but it's just a fraction divided by a fraction. So instead of doing that, I'm just going to flip my denominator, the fraction that's in the place of the denominator. I'm gonna take its reciprocal. So density is going to be, and then I'm hoping you can see that the acceleration of gravity is going to cancel. And the formula simplifies rather nicely. So we'll get that the density is equal to the weight. Well, let's have the density first. The density of water times the weight of the object divided by the weight of the displaced fluid. Now we're just going to plug in our numbers. One thing I forgot to say or to mention is that I know the density of water. Wait, was it given? No, it was not given, but it's just a quantity we should memorize. 1,000 kilograms per meter cubed. Now we'll use decimals to see what we get. And there you have it. The density of this object is 8,416.67 kilograms per meter cubed. And that's it.